Okay, so I'm going to start with the FIRESS presentation, which is the one I'm least comfortable with. I'm going to try and do justice to Matt's presentation. So I think this is the one, or is it? No, this is the one. So are you seeing it? If I do this, which version are you seeing?
Oh, you have two slides.
Sorry, you spoke all together, so I didn't understand.
It's a presenter mode, we are saying.
Okay, let's say. So if I switch like this, what do you see?
Perfect.
Okay. So FIRESS stands for the Far Infrared Enhanced Survey Spectrometer. So as the name implies, it is a spectrometer. And these are examples of spectra that you'll be able to obtain with FIRESS. So FIRESS has two modes. I'll speak later of the high resolution mode. This is the black spectrum on top. This representation doesn't do justice to the resolution, and later on in this presentation, you'll see better the spectral resolution. But the three bottom spectrum are what is going to be obtained in low resolution, and the interest of FIRESS is that really it's providing a full coverage from 25 to 235 micron by stitching together 4 spectral modules. So this is the kind of spectra we expect to be obtaining, showing you the evolution as redshift. So we'll be able to go rather deep in redshift up to z equals 5 and still be able to identify principal lines and features in the spectra. So the concept of FIRESS is really that it's made of 4 spectral bands, which are all slit-fed grating modules. Below you see in this table the separation in wavelength band, and the important aspect is that band 1 and 2, so the short wavelength band, have a constant pixel size on skywards. The long wavelength band have a pixel size that evolves with wavelength. They're all made of similar shaped arrays, so that's 24 spatial pixels in the vertical direction in this representation on the bottom right, and 84 spectral pixels. There's a gap in between these two arrays. This is a feature that's common to both instruments. All the detectors in all bands are read out simultaneously. So all 4 bands are operated and read out at all time. There's no moving part in this instrument, and in fact, there's no moving part in Primager as well. We're simplifying the mechanical structure of the instrument for effectiveness. And on the top right, you have a schematic of band 2, and all the 4 bands have a similar optical design. They're all enclosed in the 1K enclosure within an optical bench that is at 4.5K. So looking first at the center of this figure, this is the footprint of the different modules on the sky. I'll talk later of the Fourier transform module, so for the moment, ignore that gray circle. So the important thing to realize is that there is an overlap of band 2 by 2. So band 1 and 3 overlap spatially, their footprints overlap, and band 2 and 4 overlaps as well. But they are separated. So it means that if you want to have a full spectrum, you need 2 pointings, to move the source in the field of view of band 1 and 3, or band 2, and then band 2 and 4. The reason this has been associated is essentially for the manufacturing of the dichroic beam splitter, to make them as clean as possible and as transmissive and reflective as possible. So we are really separating the wavelength range that they have to split. The detectors all have this shape identified on the top right. So the spectral direction is the long direction and the short direction is the spatial direction. And in fact, here it's showing what we intend to do in terms of observation of point sources. We have a BSM that stands for beam steering mirror that allows us to move the source with respect to the instrument. So essentially, we can have chopping between positions, so that allows for background correction as well as modulation, time modulation of the signal to beat out noise components. So this is the expected sensitivity. So what we're showing, and I'll be showing that as well in Primager, is the required performance. So we're starting from the PI cases. That's what Betsy showed. And we're deriving what we require in terms of performance. And obviously, we can do also a bottom-up approach, starting from the measured performance of the components of the instrument and building what we call the current best estimate. And we are trying our hard to make sure that the current best estimate is way below the required performance. But since the instruments are still evolving in their design and we still need to measure a few elements, what we're providing for the time estimator is the required performance. So that allows you to design your cases as well as with the PI cases. So using the same performance as the one we are using. So typically this is showing the comparison for a 5 sigma 1 hour line required sensitivity compared to previous instruments such as Herschel SPAX and Spire, and on the edges of the band, ALMA and FIRESS. And this is showing you this is showing you some scaling that you can use to relate that graph to your special case. But the time estimator implements these relations, so probably it's simpler to use the time estimator to run the estimation of your observation need. Yeah, remember that you only do 2 out of 4 bands at each observation, so you need to multiply your time by 2 to get a full spectrum. And this is the mapping speed. So it's the, as you know, PRIMA is capable of scanning the sky, and so the idea is to do spectral line survey, and therefore we are also providing an estimator to let you estimate the time needed to map a certain area for and obtain the spectra of all point sources there. So these are also the relations that you can use to go from this graph to the needs of your observation. But again, the mathematics of these are implemented in the time estimator, and we will work on building up more capacities in the time estimators as time goes by. All these graphs refer to a low background condition that is typically an extragalactic field, and they refer to extracting the line emission from point source in the map. This is important because as you probably know, the background level can change drastically from extragalactic to a galactic field, and this can have an influence. Now, the complex part of the presentation, for me at least, is starting now. That's the Fourier transform module. So this is a module that we can put in the optical path to transform FIRESS into a high resolution spectrometer. You can see the resolving power that you can get. So it's pretty impressive. And the idea is that essentially you insert this module in the field of in the optical path that you see coming in from the left, and you see on the right that it goes out to the grating spectrometer. So it's a bit complicated to understand why we are combining the grating spectrometer with the Fourier transform module, but the idea is to use the grating as series of filters that allows us to map the high resolution produced by the the Fourier transform module and then stitch back the spectra into a high resolution spectrum. And this is typically what you can expect in terms of spectrum quality. This is a relatively bright source, the disk at 140 parsecs. And you can see how rich the information that can be delivered by the spectral module, being on either on water compared to Herschel or at the short wavelengths compared to the JWST. So there's a really an amazing wealth of information that can be collected on relatively bright sources, but still for which there'll be extremely interesting physics to be done. And this is a graph where Matt tries to explain, why it makes sense to combine a Fourier transform module with gratings, which I'm unfortunately unable to explain very well. Really, the idea is that each grating channel gets its own little spectrum, and then the spectra are stitched back together. So it will be data processing intensive, but again, the plan for PRIMA is that we, the PRIMA team, develop the specific data processing methods for the observing modes, and so that the pipeline will deliver the stitched back spectrum from the Fourier transform module observation. You, as an observer, will not have to do that. And so this is the high resolution mode required sensitivity. Again, I'm talking about requirement-based derivation of the sensitivity. And on this graph, Matt has shown where we think we are in terms of our current best estimate of the sensitivity. So we are below our required sensitivity. And it's providing you with the scalings to go from this graph, which is a 5 sigma 1 hour line sensitivity, to the conditions of your specific observation should you want to be using this mode. And again, remember, you only observe 2 bands at a time. So if you want the complete spectrum, you need to repeat the observation under, well, not necessarily similar conditions, but you have to adjust to the expected brightness of your source in the 2 bands. And I think that's it. So I can take a few questions, but I'm not completely sure. Maybe it would be good to record the questions, but I'm not sure I would be able to answer them.
Maybe I can ask a simple question.
Yeah.
So 2 bands, if we're trying to get the complete wavelength coverage, we need 2 pointings, right? And how much do they actually overlap and make that easy?
You see there's about, do you see that? Okay, let me see if I can put that, enlarge this. So this is the instantaneous, this big box here. Well, in fact, it's smaller than the field of view provided by the telescope, the instantaneous field of view provided by the telescope. So typically, you would need to make an offset by about 4 arc minute, 4.5 arc minute between your 2 observations. It's not necessary probably to do it with the telescope itself, but probably with the beam steering mirror. The telescope delivers a field which is about 40 by 20 arc minute, inside which the instruments select individual field of views for their array. So for FIRESS, you see those are the individual field of views of the slits of the spectrometer. And you can see that they are separated by about 4 arc minutes. So typically, in an observation, when I when I place the source in the slit of band 2 and 4, there is signal coming on band 1 and 3. They are on sky, but they are offset from the source of interest. And you need to make a second observation where either using the telescope, but most probably the beam steering mirror, which is likely to be more accurate in terms of small displacement. You need to make a shift by 4.5 arc minute to move the source to your second set of slits in your second observation. Probably when we design the operating modes of PRIMA, this will be included in the observing mode. You will say, I want to observe a full spectrum of this source, and it will bring out the set of command that includes the offset, the mirror motion to put your source back into the other set of band. But now you're estimating the time needed to make your observation, and this estimation you need to make it twice because one estimation is for only 2 bands.
Mark, can I have a general interest question? How easy would it be to observe a source with PRIMA and then follow it up with FIRESS?
So if you know a priori that you want to observe a source with PRIMA and then with FIRESS or the reverse, I think this will be relatively easy. I think I have to check. I don't know what is the angular separation between the PRIMA footprints and the FIRESS footprints. Therefore, I don't know if you need to repoint the spacecraft or you can do it with the beam steering mirror. In fact, it's maybe I haven't said that, but there's a beam steering mirror on both channels. So there are 2 beam steering mirrors in the focal plane. One is for PRIMA and one is for FIRESS. So if the footprints of the 2 instruments are such that within the accessible field of view you can move the FIRESS field of view to where the PRIMA field of view was, I think it would be extremely easy. It's just a motion of the beam steering mirrors, but it's likely that it would require a repointing of the spacecraft. We're estimating also whether we need to use PRIMA to do some peak off of sources. It's not yet completely decided whether the performance of the pointing is enough to dispense with that. Now,
Okay.
if by follow-up you mean, after having done the PRIMA observation, there are sources that you find interesting and you want to reobserve, I think it's a bit more complicated because it means that we don't know yet how fast we are going to be in processing the data, delivering the data, and then there's constraints of visibilities. PRIMA is an infrared telescope and cool telescope, and like all such telescope, it observes on great circles, and so there are visibility constraints at any time. So you may have to wait 6 months for the source to come back into visibility. And hopefully in these 6 months we would be able to download the data, reduce the data, deliver them to you, and you could plan a new observation.
Yeah, this is new observation, so this is a bit different. Now I was meaning nearby in time observations.
The thing is that I haven't said that, but PRIMA and FIRESS cannot operate simultaneously. So it's like, in fact, in fact, what I said earlier wouldn't work. Well, probably doesn't work. We haven't decided yet, for instance, if there would be a PRIMA operational day, then a FIRESS operational day, or whether we can switch from one to the other on a matter of seconds. This for the moment we haven't explored. But they are not on simultaneously.